Okay, so our last speaker is Marek Zieliński. He's the CTO and co-founder of Census. Marek has over 15 years of experience in various data science projects. He's, by education, he's a solid-state physicist. However, currently he focuses mostly on machine learning. Let me put the presentation for you, Marek. Okay, and as before, if you have any questions for Marek, if any of the things that he will be talking about you find interesting, please do type the questions in the chat. Marek, the floor is yours.
Okay, thank you. I'll just correct my camera. Okay, so welcome everyone. It's a pleasure to be a part of XAI this year. It's also an honor because we had really great speakers today before me. I have just 20 minutes, so the topic of explainability and large language models is both big and interesting, so I won't be able to cover it all. I will just go through the most notable and perhaps promising approaches, both from scientific and R&D perspective, but I will focus on one approach that I see as having the most potential for quick wins in terms of value in business contexts. And it's a bit of a paradigm shift, I think, where aspects like usefulness and practicality are important, and we accept some form of trust in AI models. So let's get through explicit reasoning and explainability in large language models. And yeah, I would like to give you a thought from Marvin Minsky to start, one of the founding fathers who coined the term artificial intelligence in the 1950s. So it goes, no computer has ever been designed that is ever aware of what it's doing, but most of the time we aren't either. So just a thought to be mindful of. A few words about me. I work in data domain for more than 15 years, doing various analytical projects, mostly getting insights and value from data. I'm mostly responsible for machine learning and AI projects and adding explainable AI elements to those projects. I worked and still work on what I call old school NLP. A few things have changed since large language models proved their business value last year after all the hype. Yet solid baseline from NLP stays relevant. And my academic background is solid state physics and data engineering. I have 6 points for today. First, I briefly go through approaches to explainability and interpretability for language models, plus the challenges that we have, and a distinction about implicit versus explicit reasoning, which I view as quite important in terms of practical implementations. If you're not familiar with it, I will discuss what it is. Following from that, there is an important question: what do we as people consider a satisfactory explanation, and how to achieve it with AI systems based on, for example, like large language models? Then just a brief look at user experience when we consider a system that is more interpretable. And finally, if time allows, a few points about balancing complexity. Let's start with a simple example of a business task. And this task is, please investigate the recent decline in employee engagement, as an example. And we get an answer with some mention of analyzing data sources and then proposed solution. And this is not very transparent. So we gave the generative AI system a task, and we have some form of RAG solution, so retrieval augmented generation. The system retrieved documents, read through those documents, and added the most relevant parts into the prompt. And then, based on the context provided, the language model performed some implicit internal quote-unquote reasoning. And then generated a few proposed solutions. And such an answer just begs for an explanation, doesn't it? Like, why those 3 possible solutions? Why not others? We heard a lot about regulation and compliance today. So what if we are forced to explain those choices by some regulation because our domain demands it? How can we do that? And one of the things that engineers do is to look into the internal workings of a system. So we can look into this internal quote-unquote reasoning part. You can argue it's not real reasoning. That's why I use quotes here. So we actually know how it works, or what are the parts in the architecture, or to be specific, how to build it. So right now, most of large language models are based on decoder-only transformer architecture, and we can look inside the neural network itself. Although it's complicated, but we can do a sneak peek. But first, so how this is implemented in the real world. And this actually looks a bit better if it's an animation, but we had to transform it to PDF. But you might have seen it somewhere. So to be precise, Gromit should actually sit backwards, because LLMs actually look to the past to predict the next word, and they usually do it very fast. So getting back to the serious part, why we might need explainability. And here in the context of knowledge management in organizations, one of the often cited white papers from IDC states that Fortune 500 companies lose at least $31.5 billion a year by failing to share knowledge effectively or at all. And you'd probably agree that most of the knowledge in organizations is siloed in different parts of the company, some key individuals or some knowledge management tools. And according to another survey from 2023 done by Unisphere Research, 36% of managers have 3 or more knowledge management tools, and almost 1/3 has no clue how many they have. So this really looks as an untapped potential for getting value out of explainability, for example, here in the context of knowledge management. And that is where AI agents based, for example, on large language models can come in, or generative AI systems powered by agents. And later on, I will show an example to combine explainability and interpretability with user interface to possibly address similar issues. So let's get back to our example and look how we can explain the answer here. And I will start with a few methods that are more general in the context of artificial neural networks. Of course, this will be a brief overview. It's short on time here, and it's not the scope of this presentation. But the first one here with implicit reasoning. So in a way, most of them are post hoc interpretability. And we have mechanistic interpretability, which aims to look into the components of the network and then build a mathematical model of what is inside, what this inside part of the network represents in the output. I will show a short example of that. Then a few methods that might be familiar from previous talks. We can use input to generate explanations in the form, for example, of feature attributions. And this is where methods like SHAP and LIME can come in. And we can use perturbation methods and treat the model as a black box, or we can also use gradient-based methods to get those feature attributions and then saliency maps. Nikolai, for example, talked a bit more about gradient-based methods in computer vision. So here we can use similar methods just for text. And then a few methods, like for example, post hoc explanation by the same or other LLM model, which perhaps is more like a justification for an answer. It's more akin to a speculation, perhaps. But in certain use cases, it might be sufficient. And I will also briefly show one recent and promising method that falls under the category of hybrid methods, combining internal representation of hidden states like in mechanistic interpretability with forcing the LLM to generate kind of an explanation. Then we go into explicit reasoning part. You can be familiar with a group of methods where we force, for example, a sequence of thoughts before the answer is given using a specific prompt templates. So approaches like chain of thought, tree of thoughts, or more complex like graph of thought. Also least to most prompting, where we try to decompose a complex task into smaller, easier tasks. And interestingly, most of those approaches were motivated by improvement in task solving. So there is a byproduct of that, which is a more interpretable AI system if we have the reasoning path. And I also mentioned approaches like React. And if I have time, a very recent from February 4th this year framework, DELMA, which simply stands for Decision-Making LLM Assistant. They build a framework to deal with uncertainty that other models and methods do not address. And there was also a very recent paper, and I won't be going into details on that one, showing that you can get outputs similar to chain of thoughts without using prompting. So just by exploring alternative top K tokens and generating alternative answers, starting from that. So instead of using just one selected token and generating one answer, we generate a couple of them based on a proposed list of top K tokens. And of course, there are many more methods that we won't be going into today. So an interesting paper from late last year from MIT, and what they found is that you can train a linear probe that inspects one of the last year layers of the neural network. Here it was Llama 2 with 70 billion parameters. And in this case, the probe was able to find representations that then could be placed on a map on the top of this picture that's representing spatial dimension. And also for historical figures, dates of artworks or publication dates of news headlines, the representation showed correlation with time. So in a kind of representation of time inside an LLM. Another method, feature attributions and saliency maps. Now we talked about it, Łukasz talked about it in terms of tabular data, for example, SHAPs. Here we treat words, tokens, or text chunks as features and calculate how each of them influences a part of the output. But the drawback is that with large language models might require a lot of computation. And this is an example from SHAP library. And what a quite recent addition that I mentioned in the hybrid part, because well, the main idea here is to do inference to generate an answer and extract one of the hidden states in the neural network, then transform this hidden state and then patch it to another inference path. So while generating another answer, we inject neuron activations from the previous answer. And with a specifically designed prompt, it's able to translate it to a form of explanation. So like in the example here from the paper, the word CEO in the original answer was representing Jeff Bezos, which makes sense in the context of the original sentence. But most of those approaches are very promising and scientifically interesting. They are also important for us to be able to debug and improve the models itself and align them better. However, this is not yet immediately practical in business context, producing satisfactory explanation. So common problems are that usually we need to know exactly what we're looking for. We operate on only a few entities from a closed vocabulary, just a few concepts that we can expect. Usually those concepts are represented by big groups of neurons, and the same neurons are used to represent vastly different concepts. So it is a challenge with generating some generic explanations. And those methods are usually very computationally expensive. And probing early layers of the network is very challenging, so it's usually later layers in the networks. So this is more like a sneak peek into the models, but very promising. Now, let's stop for a bit and consider what is a satisfactory explanation for us. So those points are based on the work of Tim Miller in his article, Explanation Artificial Intelligence, Insights from the Social Sciences. A very good work and very good baseline for thinking about interpretability and explainability that is useful and satisfactory. So a few points. Explanations usually answer a few questions, and the most important question is why. So they should be transparent, usually consisting of some observations, data sources or events, and a thought process, theory. What they found is that they should be contrastive. So we usually want to know why this particular event has happened instead of some other event. They should be selective. So we're usually not interested in everything that happened. Something that is satisfactory usually focus on something that is abnormal and highlights this part. And they are also social and contextual. So there might also be different goals of explanations that it might require different tools. One other useful analogy, in my opinion, here is the work from Daniel Kahneman, Amos Tversky, and Keith Stanovich, which led to the theory about system 1 and system 2 thinking. And if you consider an easy task like 2 plus 2, that's perhaps memorized, then you can answer very quickly, instinctive, with very little effort, and most likely unconscious. And when the task is more complex, like for example, 21 times 354, it for sure will be more rational. You need to consider the method to solve the task. It will be slower, more logical, and would require more effort. So there would be conscious reasoning steps required. And we tend to put some trust into both of those modes of thinking, even if only the second actually is currently interpretable. So let's again go back to our example. And now instead of just getting the answer, we can force the system to generate reasoning, like a form of thought process before providing the answer. And an example of that could be here, a very simplified one, just to fit it on the slide. And let's distinguish that from the previous method of asking an LLM to generate an explanation afterwards, so a post hoc explanation or a justification for the answer. So we want the quote-unquote thoughts to go first and then the answer. Because LLMs, you might have heard this term, are autoregressive. So it means that they look back at the context, even the one generated by them. So if a word is predicted, it then goes back to the input and influences next output. So if the reasoning comes first, it actually influences the probabilities of next tokens, and it influences the final answers. And this is what we want. And if we use this approach, the answer might actually be a bit different as in this example. And usually it's more accurate and more grounded. So the distinction between implicit internal versus explicit verbose reasoning is very similar to the way we treat large language models. And one approach is to treat it as a knowledge source, which it might be in certain use cases. But then it is essentially a black box, and the method of generating the answer is not really transparent, apart from the methods that you can sneak peek into the architecture itself. But we can also treat LLM as a reasoning engine. And that's not my idea. You can see Andrew Ng also talking about it. So when we ask a question, we want it to generate thoughts about understanding the task, observations about data or events, and then another thoughts that might analyze previous observations, and it's in the right side. This way we have this thought process saved for future use. So in a way, we make the AI systems more interpretable. And the more granular we can go, like the less ambiguous those intermediate thoughts could be. So we could get two benefits: better task solving ability and a more interpretable system. And let's briefly go through the most notable approaches to explicit reasoning and LLMs. We have the precursor approach, which was COT, chain of thought, introduced in 2022. A simple example of such an approach is, let's think it step by step. And there are more modifications to that, like adding reasoning examples in the prompt or other modifications. Like the next improvement to the naive COT was self-consistency, where a few reasoning paths were generated and then a majority vote was used to come up with the answer. And this slide comes from the paper that introduced three of thoughts. So a bit more complex data structure that allows to capture more interesting relations between generated singular thoughts. And one of the current prevailing approaches to implementing agents is ReACT. So a combination of reasoning and acting techniques. On the left, you have reasoning only with just reasoning traces, and actions only where actions were generated based on observations. And if you think about ReACT, it combines it into one approach where we have three important elements: reasoning traces, observations, and actions. And this is actually something that's implemented in LangChain, for example, and abstracted for you to use. And since you can also integrate LangChain to, for example, Azure AI Studio, you can also use it there. And it's currently a default approach for building agents. And if we think about an example, we would have questions and thoughts like, what is the problem? So understanding the problem, then what data or tools do I need? What are the causes? What are the possible solutions? And finally, recommended actions. And in this process, we get reasoning traces and perhaps also alternatives that can be used for contrastive explanations, which is something that we seek in explanations, to be able to compare to something other that could have happened. And just briefly, let's think about the interface to interact with LLMs, because currently we mostly use chat interface. It's nice, it's conversational, and sufficient for some use cases, but it's not really an ideal interface if a lot of contextual information is needed. So can we do better? And let's consider an event. So what if the motor on your boat stopped working and you're in the middle of a lake and don't know what to do? And then you call customer support, and the person answering the phone also doesn't know what happened and what to do. And if you think about such a case, there is a lot of context information that might be lost in a simple chat interface, but it might still be valid and useful. So normally such a breakdown of intermediate tasks like document retrieval and intermediate steps is accessible via debug mode and, for example, LangChain. But here we want to use them and keep them in the user interface, so it's accessible immediately. And the user can get a lot of useful information about the case, and the more granular the steps are in those tasks that we generate along the way, the more grounded and more factual the information can be, or actually will be. And we still get the chat as part of the interface, and whenever we need more conversational interaction, it's accessible. And we also enforce listing of source documents, and then have closed allow list of possible actions, which is important from security reason. And the action can be chosen manually by a human operator, or if we trust those actions, then those can be automated. So in a way, we make the UI and the AI system interactively interpretable in real time. I will skip a few slides because we're, I think, short on time, to the last part where we finalize the case and want to generate documentation out of it, having all those like very granular steps that we have there. And if we chose a solution, then usually we want to generate a shortened documentation. Like intermediate steps might be needed for debugging or auditory drill down. However, if you remember what Joris was saying about balancing the size of the explanation, and also what I mentioned about selective character of satisfactory explanation, then usually as a first point of contact with the case, we want something like a very focused short note, not an essay. So we can go through that. And if everything is saved, close the case, having a documentation. I will skip this part and just briefly go through a few things about balancing the complexity. So one thing is modular system design, because with current speed of developments in large language models, like the solution should allow for easy swapping of LLM models, because like a few months and we might be using something completely different. And we also need to be able to optimize each component separately. One thing, efficient retrieval methods, for example, like caching frequent queries, reasoning granularity, which is a trade-off of multi-step reasoning that can be more detailed, more transparent, but it's slower. And then we again have to simplify it afterwards. We can, of course, combine symbolic methods like knowledge graphs with natural language models, which again makes reasoning more interpretable, but again adds complexity. And let's remember that the interface for the explanation also does matter and should be tailored to the intended audience. And I just wanted to leave you with this expanded thought about the need for explainability, especially in generative AI here, language models. It's just not just a nice-to-have feature, it's really a must-have, and it's about trust, compliance, and improvement. And ultimately, it's about creative generative AI systems that are not just smart, but also have a satisfactory level of fairness, transparency, and are reliable. So thank you.
Thank you, Marek, for this very interesting speech. I don't see that we have questions in the chat, so maybe I would have just one for you. So many of the concepts which you discussed sound very advanced. Do we actually currently already have the tools with which we could build such application, or is it something like we have to wait, say, 12 or 24 months? Like, do we already have tools?
Well, I actually focused on the part that is applicable right now, because the mechanistic interpretability and the sneak peeks into the architecture are in the realm of science and R&D, and not immediately applicable. We'll probably have to wait a bit. But with the approaches of building interpretable reasoning paths, there are a lot of new developments, very nice frameworks to add. And also, most of that is already implemented, for example, in LangChain, as I said. So it's basically ready to be used. And a lot of them are built using prompt templates. So again, this is something we can also improve ourselves.
Okay, great. Again, thank you very much for your talk. And you were the last speaker today, so thank you very much.
Thank you.
And returning to the main presentation, we're done for today. We had all the speakers, we had all those talks about regulations, use cases, and explainability. That's all for today. We'll be having the conference already the next year. We'll be having other events, so check out Tensenses at follow us on LinkedIn, and so that you can get updates. And we already invite you for the next edition the next year. And as for now, have a great day and see you next time.